Thank you, Tracy. And welcome to IEEE 802.11ac, a preview of 802.11ac. I listed this passage from Charles Dickens' A Christmas Carol. I thought it was appropriate. My apologies to Mr. Dickens if he's listening in. The ghost of Christmas yet to come. Before I draw nearer to that stone to which you point, said Scrooge, answer me one question. Are these the shadows of the things that will be, or are they shadows of things that may be only? Still the ghost pointed downward to the grave by which it stood. You can all see the grave by which he stands. You may be wondering what a quotation from a 19th century story has to do with the latest, greatest revision to Wi-Fi. Well, first, 802.11ac is making some big and exciting claims. Terms like gigabit Wi-Fi, for instance. Well, happy holidays. But like a ghost, it doesn't fully exist, even though we're beginning to see equipment that uses it. And since 802.11ac is only going to be supported in the 5 gigahertz bands, this amendment may finally portend the end of 2.4 gigahertz wireless LANs, at least for advancements and innovations. But at this point, who can really say? Hi, everybody. Thanks for coming. I'm Rick Murphy. I'd like to thank Fluke Networks and the folks at Air Magnet for providing me with this opportunity. This is a chance to offer a preliminary review of 802.11ac. Please note that all the comments you're about to hear are my own. They may not be shared by my sponsors here. So, many of you have been to my presentations previously, and so you're going to see some familiar material that I'd like to build on from past presentations. I have a large number of slides. I'm hoping to get through them all fairly quickly and still have time to answer some questions at the end of the hour. So you can use the chat or Q&A features to submit your questions if you know how to do that through the WebEx interface. But you can also see my email address here in case you want to send some additional questions, or if we kind of run out of time at the end and there's something you want to follow up with, please do. Also, you can send information directly to AirMagnet at info@airmagnet.com for further follow-ups. Today's topics. So we'll begin with a look at 802.11ac, which is currently only in draft status. This is not an amendment that has been released or finished or fully ratified or published. But the reason that we're talking about it now is because I've been getting so many questions about it, both in classes and in our study groups. Some people are under the impression this is a done deal and it's out there. It's far from that. It's not finished yet, but we are beginning to see equipment come out that is using this standard. And so let's take a quick look at it, see where it stands, where it's going, and what benefits it may have for you. So that's the timeline. Then we're going to look at Task Group AC's proposed enhancements. What's going to change about AC that will be useful or not, and whether or not you think it will be valuable for your infrastructure. Then we're going to look at the new MCS indexes that come out with VHT. VHT stands for very high throughput, as opposed to high throughput, or HT, that came to us from 802.11n. Next, we'll look at 802.11n and 802.11ac channels and subcarriers. The reason that we look at the channels and the subcarriers is because this is going to be very important for design and planning of your wireless infrastructure. And then I was able to get some very preliminary equipment and do some basic throughput tests, and I'd like to share some of those results with you, even though they're very preliminary, very low level. Thought you might find some interest in that. And then to wrap things up, we'll have some kind of a slide that covers some conclusions that we can make about 802.11ac at this early point in time. Okay, so here's a screen scrape from the IEEE 802.11 Working Group Timelines page. You can see the URL down here. It's a handy URL if you want to check on the status of any of the 802.11 amendments in process. If you look at the very bottom, I've put a red border around the 802.11ac project. And as you can see, this is called very high throughput. It exists below 6 gigahertz, and it's currently in draft status version number 3, which is fairly early in its development process. If you look at column 7 from the left, it's titled PAR Expires, and PAR stands for Project Authorization Request. If you look at the date there, you'll see that it is set for December 31st, 2012. Now, just to clear up some misconceptions, that date does not necessarily mean that's the date that this standard will be completed and finished and published. Instead, that just means when the PAR, the project itself, its charter will expire and have to be renewed, but that can be extended for whatever amount of time is necessary to complete the project correctly. So we're expecting this project to continue on into next year, and what we're seeing now is very, very preliminary. So as I said, we're only on draft 3, and we can expect to see some changes. The reason I mention this is because this is kind of similar to what happened with 802.11n years ago. And at first, there was a flurry of equipment coming out on the market. People were purchasing that equipment thinking it was a done deal, and they found that some of the equipment would not be upgradable when the final standard was released. I don't think that's quite as big an issue with this version. 802.11n had a lot more work to do than 802.11ac. AC has a lot of the foundation material has been created, and now it just seeks to improve, enhance, and expand on that work done in Task Group N. So I think we're going to see the final ratification of this standard fairly soon, probably within the next year. But bear in mind, it could be more towards the end or middle of 2013 before you see that happen. One more important step, we would like to see certification from the Wi-Fi Alliance come out to assure us of cross-vendor compliance with the standard. So those are a couple of mile markers that you should be looking for before you can really jump on board of this standard and really start, recommending it to others and things like that. Now, for your own use, I think it's great to get involved early on, become an early adopter, see where this is taking us, and make use of the really nice features built into AC. But as far as recommending it to others or as an early implementation, I think it's a little soon out of the gates to start with that. So let's just use this session to kind of get a preliminary idea of where AC is going to take us. So here are some of the proposed enhancements with AC. Now, I have personally broke this off into 2, I call them phases. And these aren't formalized phases. What they are, they're just kind of general phases. So I kind of broke it down into that which will occur now and up to the point where the standard becomes ratified and published, and that which happens after that full certification process is completed. So if you look on the left-hand side, these are things that are coming out right now. And this is stuff that will be happening here in this year and in the next year, and we can expect this to be available on your vendor shelves currently and in the near future. But the items on the right-hand side, that's probably a little bit further down the line, possibly a year or more out before you start seeing these features commonly available. Let me go down the list, starting on the left. So right now, 802.11ac is being offered on certain vendors' equipment, and it will operate in the 5 gigahertz band only. So full support for 802.11ac, 5 gigahertz only, no more 2.4. So that's what I was kind of talking about with that ghost slide. This could spell the end of any new innovations for the 2.4 gigahertz wireless LAN technologies. There's reasons for that, and we're going to talk about that in just a second. Also, notice on the next bullet down, 802.11ac right now will support 20 and 40 megahertz bonded channels, such as we had with 802.11n, but also will support a new level of channel bonding called 80 megahertz. 80 megahertz is a very wide channel. That gives you really a huge amount of bandwidth to work with. Below the channels is the number of spatial streams. Now with 802.11n, the task group N had specified 802.11n out to a number of 4 spatial streams. So this isn't really groundbreaking here with 802.11ac, except there's some other features added in with that. But how 802.11ac uses these spatial streams, there's a little bit of naming convention changes that you should be familiar with, and some minor changes that I'd like to go over with you. 802.11ac will also support a new modulation level of 256 QAM. So that adds on to our existing BPSK, QPSK, 16 QAM, and 64 QAM. Gives us some additional options for higher throughput. Even though it's only 2 additional bits per modulation symbol, it actually adds up very quickly. And that's a very nice feature. So those first 3 features there, the larger channel bonding, the number of spatial streams, and a new modulation technique are probably the biggest, most important features of 802.11ac. That, along with the idea that it will only be used in 5 gigahertz bands. Next, below that, you see something called standardized transmit and receive beamforming. Now, 802.11n really kind of broke ground on beamforming, but it wasn't implemented by a lot of different vendors because there was some leeway on how that would be implemented. So 802.11ac is going to attempt to standardize that a little better, make it easier for different vendors to take advantage of the robustness of transmit and receive beamforming. With 802.11n and the first wave of AC, we will expect to see single user, multiple in, multiple out transmissions. That's what we've had all this time up to this point. But in the future, you can expect to see multi-user MIMO. And that is the case where a transmitting station transmits information that can be received by multiple unicast addresses at the same time. And that's pretty advanced, pretty good stuff there. So the stuff on the left, all these features here, the ones that are coming out right now, we can see this in certain vendors' equipment on the shelves today, and you should expect this equipment to be suitable for SOHO or power user only. It's not really up to scale, up to grade for enterprise use yet. But when the new features are released, probably in end of 2013, over the border to 2014, we're going to see some additional features, including not just 80 megahertz bonded channels, but 2 80 megahertz bonded channels that gives you the total bandwidth of 160 megahertz, and these channels don't have to be contiguous. There's also the option to go to 160 megahertz channel itself, but that would be a contiguous channel. So we'll take a look at how that all works and lays out. In addition, the full ratified version of 802.11ac will offer up to 8 spatial streams, and those have been fully designated, and we'll take a look at those coming up. Let's begin here. Now, those of you who have been with me before have probably seen this slide. I like to use this. This is a spectrum analysis capture over time of OFDM symbols being transmitted. So we see the grand mesa of OFDM, and we see how the center frequency in the center has a little bit of a null drop there. We see the edges where it tails off, and we refer to this, or we can refer to it, as a mask or a spectral density mask. Using this mask idea, a few years back, I created a channel simulator to allow us to lay out the channel coverages with 802.11 technologies in both 2.4 and 5 gigahertz. Probably most of you are familiar with 2.4 gigahertz and the idea of using the 3 non-overlapping channels centered at channels 1, 6, and 11. Okay, so here we see the spectral density mask overlaid over 20 megahertz masks on the screen. So if you were to look at this same frequency layout, this is the 2.4 gigahertz ISM band where Wi-Fi originated, and if you were to overlay one of the new 802.11ac 80 megahertz channels, here's what that would look like. And this is the reason, primarily, why we're not going to plan to use AC in 2.4 gigahertz, or if it is implemented some subset of AC, then it won't have anywhere near all the functionality that we will see in the 5 gigahertz range. And it's because there's just not enough bandwidth there for this high-powered technology. Let's take a look at the MCS, modulation coding schemes. Now, on the left is a chart that I shared with everybody in a previous webinar called 802.11n. And in that webinar, I kind of went over all the different features here. I don't want to kill you with all this stuff, all the details. Just look on the left, and you'll see on the chart on the left where it says MCS index, you'll see that they are numbered 0 through 31. And what really happens is every 8 modulation rates, we reuse them again. The only thing that changes is the third column from the left, the number of spatial streams. So, for instance, if you look at MCS index 0 through 7, you'll see we go BPSK, 2 QPSKs, 2 16 QAMs, and 3 64 QAMs. But then those repeat and repeat and repeat all the way down to 4 spatial streams. The reason I wanted to point that out is now look over on the right-hand side. You'll see the same chart, but I've added in the new VHT, very high throughput MCS index rates. And those are in gray. So everything in greenish blue is the older technology, 802.11n. Everything in gray is what's coming to us from 802.11ac. And one of the things we talked about a few minutes ago was the addition of the new 256 QAM modulation rate. And you can see that following the HT-MCS index number 7. And that's just blank. And the reason why is because the AC group has decided to change those modulation coding scheme index numbers just slightly. But it could be meaningful to you. A lot of us have become used to the idea of mentioning a modulation coding scheme by its index number. For instance, in the old 802.11n days, if I were to say MCS index 15, we would know that that meant 64 QAM 5.6 coding rate on 2 spatial streams. But with 802.11ac, it doesn't mean that anymore. If you look on the right-hand side, look how AC has changed those index numbers. They now go from 0 to 9, and then they repeat over and over. So now we have to have another way to identify the different modulation schemes, and the way to do that is to use the VHT index number along with the number of spatial streams. So, for instance, if I wanted to say the old MCS index 15, then I would say VHT MCS index number 7 on 2 spatial streams, and we'd have the same thing. Okay, a little bit confusing there, but that's the way it's going to be going forward. So these slides are useful. They may be kind of busy looking, and you might be wondering why I'm spending time on them. These charts are really useful for troubleshooting. I can tell if I just know the data rate that I'm connected at, and if I can find it on this chart, then that tells me everything else about the current session that this client or access point is involved in. It tells me the channel width, it tells me whether short guard interval is being used or not, it tells me the type of modulation and the number of spatial streams. So it's very useful from a troubleshooting and a performance tuning ideology. Okay, next we have a quick rundown So let's jump over to 5 gigahertz. This is where 802.11ac is going to be most useful, and take a look at some traditional layouts. So here we have the WITS channel simulator on 5 gigahertz, and I've laid out all of the possible 20 megahertz channels in the 3 5 gigahertz unibands. And as you can see, if you counted each and every single one, each possible one, including the very highest ISM 20 megahertz channel, channel 165, there's a potential to have 24 non-overlapping 20 megahertz channels. Let's take any one of those channels, for instance, channel 36, upper left, and take a closer look at it. Here is how OFDM uses that channel. So OFDM, orthogonal frequency division multiplexing, which is the basis of 802.11a, 802.11g, 802.11n, and now 802.11ac, takes the channel that it's been given and uses a special mathematical function to divide that channel up into separate subcarriers, or tones as they're sometimes called. Each one of these tones or subcarriers is 312.5 kilohertz wide. So if you take a 20 megahertz wide channel and divide it by 312.5, 64 subcarriers. But not all of the subcarriers are used for user data. There are some subcarriers reserved at the lower and upper ends, and those are to provide some guard subcarriers, some isolation and insulation from the channels surrounding it, next to it, I should say adjacent to it. And some of the channels are set aside as pilots, and those pilots are meant to help with training, and synchronization can also be used to help with modulation references. So this is our standard, both 802.11n and 802.11ac OFDM subcarrier layout. Now this was slightly different than what we used in A and G, but the only difference is the number of guard carriers on the ends. Now let's take a look at 40 megahertz channels in the 5 gigahertz range. So here with the channel simulator, I've laid out the possible 40 megahertz bonded channels in 5 gigahertz. And looking at this, it looks like you can get, looks like about 11, I think. Yes, 11. So there's 11 possible 40 megahertz channels in 5 gigahertz. Let's take a look at the subcarrier layout inside one of these 40 megahertz channels. I'll take channel 36 and 40, and we'll look at the subcarriers. So here is the subcarriers. If you have a 40 megahertz channel and you divide that by the bandwidth of each individual subcarrier, 312.5 kilohertz, you'll find that there are 128 subcarriers. So another name for a 40 megahertz channel using OFDM is OFDM 128. Here is how OFDM 128 divides up the subcarriers. Not to kill you with this, but it's really good to know, I think, what's going on here at the physical layer at the lowest level. And each one of these subcarriers that is not grayed out is a candidate to carry user data, and that individual subcarrier would be modulated at the bit rate of whatever the environment will support. So with 802.11ac, if the wireless interface will support 256 QAM, then each one of those subcarriers is modulated with 256 QAM. Another way to say that is each one of those subcarriers is modulated to infer 8 bits of information. Notice that there are more pilot subcarriers used with the 40 megahertz channel. We'll see that continue through all of these. So next, let's look at AC only. So these last two I showed you, those were common to 802.11n and 802.11ac, but now we're going to go into new territory. 802.11ac has defined 80 megahertz channel bonding in 5 gigahertz, and you can see here on the channel simulator where it's possible to have 80 megahertz channels. There's a caveat to this. First of all, let me show you, in order to get 80 megahertz channels, obviously you would have to be able to have 4 20 megahertz contiguous channels. Okay, so we can use 36, 40, 44, and 48. We could use 52, 56, 60, and 64, and like that all the way up. Many of you are familiar with the unibands used in 5 gigahertz, and you know there are 3 bands. There's the lower band, or Uni 1. That's the one we see at 36, 40, 44, and 48. And there's the upper band, Uni 3, which is 149, 153, 157, 161. Those 2 bands are available pretty much to everybody to assign statically. But the ones in the middle, what we call Uni 2 and Uni 2 Extended, are under control of an automated routine known as DFS, and that's to avoid any contention with possible radar sites within your area. So you don't necessarily have the ability to enable static control of the channels in the middle uniband. That may be an issue with 802.11ac, something we're going to have to explore. I don't have a good idea, a good feeling, good understanding of how or even if we'll be able to use 802.11ac in the DFS areas. So that's one of the many questions that we're going to need to work out. It may work just fine, but you couldn't go in and assign it automatically. That's maybe not such a big issue, but it's something that we should look into for an upcoming session possibly. Okay, so you can take, of course, the other 2 statically assigned channels, in Uni 1 and Uni 3 with no problem. Here's what the subcarriers look like. Now that's getting kind of small, I know, but I think you can still get the idea here. So now we have 4 contiguous 20 megahertz channels. We've got 36, 40, 44, and 48, and notice that things change. When you bond channels together, you don't just stick them together at the edges. You actually renumber and you refabricate the entire OFDM structure. So take an 80 megahertz channel, divide it by 312.5K, and you'll find that there will be 256 subcarriers. Thus, another name for an 80 megahertz channel is OFDM 256. With OFDM 256, you'll find 8 pilot subcarriers. You'll find guards on the end. You'll find 3 at DC in the center. Everything else can be modulated up to 256 QAM to deliver user data. This is how we're getting these high performance levels. Okay, now, a new feature in 802.11ac probably won't come out until phase 2 is the ability to take more than one 80 megahertz channel, bond it together. But there is something that's kind of interesting, and that's the idea that with 80 megahertz channels, they don't necessarily have to be contiguous. They could be separated from each other and still give you the effect of a full 160 megahertz channel. So that's a new feature we're going to be looking for. Here are 2 examples where you could take an 80 and an 80 and use them together in an 80 plus 80 mode to get 160 megahertz of bandwidth. Here's what the subcarriers would look like on that. And again, it's just as if they were isolated 80 megahertz wide channels, but the standard 802.11ac does all the heavy lifting and figuring out which bit streams go to which subcarriers and things like that. Interesting, I think. There's also the ability in the fully published version of AC to support 160 megahertz wide channels. Here's what that's going to look like in 5 gigahertz. At this point, even 5 gigahertz is starting to feel the pain. 5 gigahertz, we only really have 2 possible 160 megahertz wide channels. There is an ability, and notice we would have to use the DFS channels in either case, but there is an ability. It would be possible to put a 160 megahertz wide channel that began at channel 140 of Uni 2E and went 140, 136, 132, and down that way. So 8 channels that way. That's a possibility too. I didn't put that into the channel simulator yet. I just wanted to give you a taste at this point of how it will work, but just know that that's another option. Here's the subcarriers on that. You can barely even tell that is individual subcarriers, we'd have to zoom in to be able to see this. So yeah, we take 80 20 megahertz wide channels and bond them together. We reset the center of the OFDM modulations, and if you have 160 megahertz wide channel, that will give you 512 subcarriers, all of which, except the nulls, will be able to carry user data. Notice that will have 16 pilot subcarriers, and here's the placement of the pilots within the OFDM 512 transmission. Okay, that's enough on the technical side. I'm going to bring it up a notch here, and thanks for sticking with me. For some of you, maybe that was a little too technical, but for some of you, I know that is information you can use for troubleshooting, design, planning, and tweaking. So let's get into a little bit of a high-level discussion now. So how does this affect you? So why do you care? Is this something that's on the horizon, as I've said, or is it something that you can take advantage of right now? Well, here are some current 802.11ac chipsets in production. You'll see several different vendors on here, and some of this equipment is available on the market right now or will soon be available to you. Again, just as a little bit of a disclaimer, I'm not recommending that you go out and purchase this pre-draft or pre-standardized equipment for anything other than personal satisfaction, to become an early adopter, to learn the ins and outs of the standard. Again, it's not something that I think is ready for prime time, but it does have some interesting features. And the way I know that is because I was able to purchase this particular piece of equipment. Because of the premature nature of 802.11ac and the preliminary methods I've used to go in and look at it, I'm not going to mention any vendors' names at this time. And the reason for that is not because this equipment isn't good. I was very impressed with it so far. It's just that I have not had enough time or opportunity or equipment to be able to perform full laboratory bench tests and real-world practical tests to see whether or not my results continue on over various equipment. So quick capture, what I'm about to show you, I had real good results using this equipment from a very, very, very well-respected and well-trusted vendor. You can purchase this equipment today. I did. And I used some 802.11n legacy client devices to connect to this particular 802.11ac based access point, and I'm going to share some results with you on what I found, but again, a disclaimer, I can't say for sure. I don't have enough detailed information and proof to say that all 802.11ac access points would result in this, or that even another one of the same model would do the same thing. So again, preliminary, but I think the results are interesting enough to share with you. So I took this access point. I went into the user interface just to see what it was capable of, and it says here on the vendor, at the highest modulation coding scheme available, this will go up to 1.3 gigabits per second. That is 1,300 megabits per second. So I was able to determine the chipset. This is a Broadcom BCM4360 chipset built into this equipment. So I went out to Broadcom, looked at their specifications, and I found that this equipment is capable of dual band in the 2.4 gigahertz, completely compatible with 802.11n or HT. In the 5 gigahertz, it will support up to a subset of VHT, very high throughput. It's capable of doing 3 spatial streams. It can support 80 megahertz bonded channels and 256 QAM modulation rate. So these are very advanced features. You will not find the 80 megahertz to 256 QAM in 802.11n. For that, you have to go to 802.11ac. In addition, this particular chipset supports the AC compliant transmit and receive beamforming options. So hopefully that will become standardized, and we'll have clients that can support that too for even more robustness. In addition, low density parity check, LDPC codes can be used. These are more robust in long distances than the convolution coding typically used in 802.11n. So the maximum 1300 megabit connection speed, I wondered to myself, okay, you're saying 1300 megabits per second, how do you get there? So using the information from the chipset vendor and looking at my chart on the right, I'm looking to see what the VHT-MCS index for 1300 megabits would be. And it's confusing because look at all the numbers. Can you pick it out anywhere? Yeah, I see a 1300 megabits per second, but how do I know that's the only one? Well, that's why I made this chart active. So this chart, by the way, these charts are available to my members of our performance engineering study group only at this time, but if you are interested in looking at these up close or testing them out, just send an email to swilliams@wirelesstrainingsolutions.com, and he can fix you up with a link to test out these active charts. What I mean by that is on this chart, if I click on 1300 megabits per second, then it shows me any and all of the types of methods that you can use to get to 1300 megabits per second. And using this, I see, okay, the first one would be VHT-MCS index number 7 on 2 spatial streams using 160 megahertz channels. So we know that this vendor can only do 80 megahertz channels, so that can't be it. The next possible one is VHT-MCS index number 9 on 3 spatial streams, and that's an 80 megahertz channel using short guard interval. That sounds like a possibility. What's the other choice? That would be VHT-MCS index number 8 on 80 megahertz channel, but it needs 4 spatial streams. So it must be the second one we talked about. MCS index 9 on 3 spatial streams with 256 quantum 5/6 coding rate to get 1300 megabits per second. That's the max of what this AP can do. So now, and just a quick take, I just saw a message pop up real quick. Sorry, I'm not seeing those for very long, but it was just, can we talk more about SGI, short guard interval? And I put together the 802.11n web session a few months back, and we went into quite a bit of detail about SGI. So if you don't mind, can you ask Scott, either Scott or Joey Kuehl at Air Magnet, to send you a link for the previous webinar? And there's good detail on short guard interval there, okay? Okay, moving on. So now here's some real-world tests. So I set up the access point I showed you a few slides ago. I set up fairly nearby, a few feet away, with 3 different test pieces of equipment. One was all of these are 802.11n only, and one of them would support 3 spatial streams. One could only support 2 spatial streams. One could only support 1 spatial stream. I connected and then used my favorite iPerf tool to do a throughput test, because remember, connection speed and actual throughput are 2 different things. And here's what I found. So in the first speed test, using one of my favorite laptops that has 3x3 transmitter receiver, it was capable of doing 3 spatial streams, and this connected right up to the 802.11 AC access point with a connection speed of 450 megabits per second. Now that's not that common. We've got 3x3 equipment out there, but to actually see client devices connecting at 450 megabits per second, that doesn't happen all the time. A lot of times you'll see it connecting at a much lower rate than that for whatever reason. But when I powered this up, connected it to the AC access point, pow, right in at 450 megabits per second. That's good. Notice that would be HT-MCS index number 23. And the reason we're using the HT indexes, the ones on the left, is because my client devices can only support legacy 802.11n. By the way, I love saying 802.11n legacy devices. That's very cool to me. Okay, so 802.11n is now legacy, great. But looking down here, MCS index 23, 64 QAM, 5/6 coding rate, 450 megabits per second. You know what? That is the max for 3 spatial streams. It doesn't get any better than that. So let's take a look at my next candidate. Notice the throughput, 252 megabits per second. So I jumped back on you. I forgot I hadn't mentioned the actual throughput, which is significant. It's one thing to connect at 450 megabits per second, but to actually pass data through anything at 50% of the connection speed, we think that's good. If it's even close to 50%, then we're pretty happy with that. But when it goes over 50% like it does here, we're very happy. We're doing little dances in the street. So 252 megabits per second is well over the actual 50% of the connection speed. Very, very impressed with that throughput. Next, here's a laptop with only a 2x2 transmitter receiver. So this device is capable of connecting using HT-MCS index 15, and that's what it did. That would be the absolute maximum it could connect at. If you look at the maximum spatial streams on Legacy N, it's 2 spatial streams. MCS index 15 is 64 QAM 5.6 coding rate on a 40 megahertz channel using short guard interval. Sure enough, this laptop connected to the ACAP at the max Legacy N data rate. Then, to test that, is it just connected at that speed? Is it just saying that? Well, no, because I passed traffic through it 157 megabits per second. I think well above the 50% rate that we would hope to get, and to me, that's very good. I'm not saying that you can't do this with 802.11n. Certain pieces of equipment, some very good pieces of equipment that are based on 802.11n could probably hit this too, but you don't see it this often. Usually you see something less than 50%, even when it does connect at the full rate. And one more test, and this was a 1x1 tablet. So this tablet had 1x1 MIMO, capable only of a single spatial stream and capable only of 20 megahertz channels. So this one I didn't get a definitive answer for. When I punched in 65 megabits per second, which is what my connection speed was, knowing that it's 802.11n only, so I can ignore everything in gray, and knowing it could only support a single spatial stream and could not support 40 megahertz channels, that kind of narrowed down my search. But I wasn't able to determine if it was MCS index 6 or 7. In order to do that, I would have to actually do a protocol capture and go in and look at some decodes and see if I could figure out whether that was using 6 or 7. But the throughput on that, again, better than 50%, 36 megabits per second. This is a quick take, and I'm not prepared to defend this. I'm not prepared to make a blanket statement. I just want to give you a heads up. I connected one of my better, I would call it power user grade, 802.11n, 5 gigahertz, 3x3 access points in the same placement. I just put that AP in the same place, powered it up at the same power levels on the same channels, connected with those same client devices, and in every case I got 1 or 2 levels down on the connection speed. And the throughput was equivalent to that drop. So in other words, where I had 450 megabits per second on the 3x3, my connection speed on the Legacy N access point dropped down to 324. And we kind of expect that. So that's not a slam on N. It's not even a statement that I think that you should run with. I just wanted to give you a heads up. What I'd like to do is have you go out and do some of these tests too and get back with me, and let's review these results and see if 802.11ac is a winner. I think it may be. Okay, so I know it's a quick take. These lunch webinars, it seems like I'm always breathless and running to try to get through them in our allotted time, and we are in pretty good shape today. So let me just run over these conclusions. We'll wrap this up, and I think we may have time for a few questions on here. So first of all, conclusions. I think 802.11ac is too new for me or you or anyone to recommend to someone who's going to purchase equipment. Let's give it some time to mature and grow, but I am excited about it. I think that there's some real possible benefits here. And it's not going to be a huge expensive change either. And it's going to be hardware in many cases, but sometimes some of the vendors are building their equipment now so that you can do even hardware upgrades without doing a full forklift replacement. Next, the preliminary tests that I've received so far and have performed with 802.11ac, and that's coupled with legacy 802.11n clients. And let me mention here, I don't have any 802.11ac clients. There are some client devices out there. They're rare. I'm not sure about cross-vendor compatibility. Most of the clients either take the form of a full PC or tablet or phone, or they, which is difficult to do, testing on. And the other choices are bridges that are out there. And none of those really satisfies my requirements. I'm looking for access point to client station types of connectivity, and what are these results? I want to know whether or not your laptop or your tablet is going to see an improvement when it connects to 802.11ac. I'd love to have the AC clients as soon as they are available. I'll be jumping on that. So to finish up that statement, so coupled with legacy 802.11n clients, I have seen good or better connect rates and actual throughput speeds than I have seen with 802.11n alone. Again, it has not been verified across multiple vendors. Take that with a grain of salt. Let's use this as a starting point and go forward with testing and see whether or not this is the winner we think it is. 802.11ac will work best when there's wider frequency ranges available. So that kind of leads us to think that maybe 2.4 gigahertz Wi-Fi, I'm not saying it's going to die out, but I don't think it's going to be able to keep pace with the future. And for that, we're going to need all of the channels in 5 gigahertz. And hopefully we'll get more, because when we start using 160 megahertz wide channels, you're going to be able to see advantages there. We can keep growing. We can keep adding more radio chains. We'll have 8x8s in a number of years. That's not very soon, but someday there may be 8x8s, and people are crying out for more. And in order to do that, we're going to need more channels. So 802.11ac appears to have better connectivity for distances, but I haven't had a chance to prove that yet. So the reason I'm saying that is because my close-in tests are all showing at the very highest modulation coding scheme rates. That would make me deduce that I should be able to go further from the AP and still have very, very good connect rates. And that would be the subject for an upcoming webinar, possibly, if anybody's interested in hearing about that. Now, a couple of questions that I would like to, these are not my questions. I borrowed these from one of our members of our performance engineering study group. That's James G. And James, thanks for these last two questions. And these are things that I'd like to think about, and you may want to too, especially in the enterprise. How will the future use of more than 3 radio chains affect an enterprise power over Ethernet budget? So how much power is going to be required once we start going up into not just 3x3, but 4x4 and higher, 5x5 and up? How is that going to hit us back in the enterprise in the closet for power over Ethernet? And his other question, I think, is a good one. Will single-channel architecture play a part in the evolution of 802.11ac? Is there the possibility that we could go to the single-channel architectures in use by some of our favorite vendors who make this type of equipment? And will it give us an advantage or not? So there's just some questions we'd like to explore. If you have some further questions, let's see if we can take a look at those. I think I have one more here, and that is just a summary. So in this brief discussion, we looked at the 802.11ac timeline. We took a look at the proposed enhancements that are coming with the HT, which is very high throughput. We looked at the 802.11ac modulation coding scheme indexes and how they're different than the old 802.11n HT modulation coding scheme indexes. We've kind of got to change our terminology there. So if you're like me and you're used to spouting out MCS index levels, need to make some changes how we refer to that now with AC. Then we took a look, and thanks for walking through that with me. We took a look at 802.11n and 802.11ac channels and subcarriers, and I believe it's very important to know how OFDM is being handled and used within your channels. So I've just given you some brief information there, but we can build on that for next time. So next time we have one of these sessions, I'm going to be able to say, okay, we already looked at the subcarriers in a previous. Now we can build on that, and let's go forward with some other things, like how does the modulation work on each one of these subcarriers. And then I did some preliminary, and I want to emphasize the preliminary part of this. I did some preliminary tests on some equipment and had pretty good results, which may or may not be proven in the future as being global. So I'd like to reserve judgment until I have a little more time. But I do encourage you to try it too. I think it's definitely worth the try. And then we had our conclusions, and I think that's about it. Okay, so thanks for attending, and I appreciate your kind attention to that. And I always enjoy these. I'd love to hear from you later on, so feel free to shoot me emails. And let's see if we can take a look and see if there's any questions here. And I'll do my best to get through these. If for some reason we run out of time, which we've only got about 5 minutes left, feel free to resend that to me in an email. Okay, in the chat session, let's see what we have here. Please elaborate on SU-MIMO versus MU-MIMO. And that's good. I want to devote a little more time to that. But single-user MIMO is what we have now. It just didn't have a name up until 802.11ac. So single-user MIMO, one access point speaks to one client. One client speaks back to one AP, or in the case of an IBSS, one client station communicates directly to another client station. With multi-user MIMO, which won't be available for well over a year when AC is fully ratified, the enterprise grade version, then an access point can transmit up to 4 different transmission frame segments to 4 separate receivers, all with one transmission. So that's one transmission, 4 different users get 4 different pieces of information. Now, that doesn't necessarily have to be an access point, but from what I can read in the standard so far, that's all that's being defined at this point. So we want to see a little bit further on whether or not client devices can actually make use of that going back to the AP. I believe it's, at this point, AP out to the client only. More on that coming, though, and that was from Chet. Oh, hi, Chet. I remember you. You've been with us several times. So what Wi-Fi, sorry, just clicked on something and it disappeared. Which Wi-Fi version is being used in the wireless receivers in a particular vendor's name, and is it standards compliant? For that, Chet, I would have to research that. I don't know about that particular vendor's product. Haven't heard of that one before. Interesting, though. I'm going to put it on my list and check into it. And if you have an email address registered, or if you'll shoot me an email address, if I can find anything out about that, I'll be glad to share that with you. From Howard, will AC have protection mechanisms built in like N has? Yes, absolutely. So what that means, that's good and bad. So when AC fires up its protection mechanisms, that means that it will be able to operate in a less than greenfield environment. You'll be able to use 802.11ac in the same arena that you can use 802.11n, 802.11a, and like that. So that's good from that perspective. Will the protection mechanisms have an effect on throughput? As always, yes, because it's additional overhead, and that takes time. So the reason it's good to use protection in a mixed environment is because it saves you from having a high number of collisions. If you didn't use the protection, then you would have collisions. You have to recover from collisions. Generally speaking, that's worse than the amount of overhead you devote to the protection mechanisms. Okay, so short answer to your question, yes, it will have protection mechanisms. And let's see, the 64 QAM or 256 QAM has a substantially higher SNR requirement. Yeah, see, this is why I want to. I can easily do an hour on this. And so, you sound like somebody who is planning to do network design, and you want to know what the SNR requirements for this. And I have all this preliminary information, and it is a little bit higher than what you would see with 802.11n, especially 256 QAM. And not just that. Also remember, every time you double the size of your channel, when you go from 20 to 40, a 40 megahertz channel has twice as much noise as a 20 megahertz channel. Now you double that channel out to 80 megahertz, that's going to have twice as much noise. The noise floor is rising by 3 dB over what you had in a 40 megahertz wide channel. Same deal when you go to 160, it doubles again. It's another 3 dB noise floor up, and that's just the nature of the beast. So, of course, we're going to have different SNR levels for the different modulation schemes. Good question. That's one I can really sink my teeth into, Howard, but I need more time to devote to that. I got to get moving. We're running out of time again. I like that. A few more words about spatial streams. Ted, I wish I had more time on that. I think I did 2 802.11n presentations where we discussed the spatial streams, I think, in pretty good detail. Please check with either Scott or Joe to review that and see if that answers your questions on spatial streams. If not, shoot me an email. I'll be glad to go over that with you one-on-one. And what can be said about the ability of 802.11ac to penetrate natural barriers? See, the 5 gigahertz frequency ranges have their innate capabilities of passing through obstructions, so that's where we start. But 802.11ac transmission mechanisms appear to be more robust. Now, whether that's with some beamforming tactics or whether it's some other issues at play, I am not ready to make a statement on that. So, again, Chet, on that one, good questions. You can say 802.11ac will have at least the same characteristics of 802.11a or any 5 gigahertz technology like 802.11n and 5 gig. But I believe the protocols at layer 1 and layer 2 will make it more robust. I think you're going to see better penetration, but I can't prove that yet, so don't hold me to that at this time. And the initial commercial applications for 802.11ac, I believe, are just power users. This is going to be for video conferencing. Here's the thing. We've got BYOD. We've got everybody bringing their own devices into our infrastructures. And it's becoming common practice to use FaceTime and different types and Skype, two-way video conferencing. And many times this is going over our wireless LANs. And when it goes over our enterprise-grade wireless LANs, has an effect on our business users, on their production. And so I believe that these types of applications, if we don't do something, are going to begin to grind our production 802.11 and Wi-Fi networks to a halt, and especially our QoS-reliant types of networks. So we need something like 802.11ac to improve the speed and to improve the robustness, and hopefully that will improve our QoS and our user experiences. And with that, I'm so sorry that we are out of time. Again, I always enjoy these sessions, and I can't say thank you enough for giving me this opportunity to share my thoughts and viewpoints with you. Love to hear from you. I will attempt, in the case where the further questions that I haven't answered, if there's an email address or for a way for me to get back to you, I'll attempt to answer these. And if you don't hear from me, that just means I didn't know how to get back to you, so please just shoot me an email to rmurphy@wirelesstrainingsolutions.com. And one more time, I want to thank Fluke Networks and you folks at Air Magnet for putting up with me, giving me this soapbox to stand on and spout my viewpoints. Again, thanks so much. I hope to see you again. Possibly we'll have another 8211 AC session. And happy trails. Good luck to you. Bye.